principles of ODE applied to geometric problems. Principles of ODE applied to geometric problems. Suppose I have a curve something like this, y equal to f of x. Is it audible there? Right? We have a curve y equal to f of x, suppose. Suppose if I take some point P on the curve, some point P on the curve, at which suppose if I draw a tangent, this tangent intersects x-axis at a point. Let that point be T. The length PT is also called as length of tangent. The length PT is also called as length of tangent. It's a length, basically. It's a tangent's length. So whenever we say what is the length of the tangent, at any point you draw on a curve, you just extend the tangent to intersect x-axis. So from the point on the curve to at which it intersects x-axis, we call it as length of tangent. Similarly, suppose if I draw a normal at that point, this is 90 degrees. The normal intersects x-axis at a point, then Pn is called length of normal, length of tangent and length of normal. Of course, the line's intersection with x-axis is something which we are looking at, not with y-axis. It's all about x-axis. Now, suppose if I drop this point here onto x-axis, suppose it is q, then this length TQ is called subtangent. This is tangent, this is subtangent, and this length TQ we can even treat it a length of subtangent, and the length QN is called subnormal, subtangent and subnormal. In fact, they are nothing but subtangents and subnormals are nothing but the projection of tangent on x-axis. Projection. I think everyone knows projection. What is projection? Okay, suppose from that side, if you see this length only, its projection on x-axis would be this length. Okay, which is called as subtangent, and the projection of length of normal on x-axis, we get it as subnormal. Okay, and for these subtangent, subnormal, tangent and normal, we have certain formulae we have. Just take down the formula. We can always deduct those formulas. It's very easy to deduct those formulas because they are just lengths. Length means they are just the length between 2 points. And this point, suppose if you say x naught comma y naught, and we have assuming that there is a slope. Slope obviously is dy by dx coming from the curve. Y equal to f of x, we will get dy by dx at the point x naught comma y naught. So y minus y1 equal to m into x minus x1 gives me the equation of this straight line. Where it crosses x-axis, put y equal to 0. Whatever x you get is the point at which it crosses x-axis. Similarly, to get the equation of normal, what is the equation? Y minus y1 equal to minus 1 by dy by dx. Minus 1 by dy by dx into x minus x1, which gives me equation of the normal line. And just see where it intersects x-axis by putting y equal to 0. Okay, you will get all such points. Okay, and those points, if you take the length between those 2 points, what you get is these expressions that we are going to discuss. And this is all about Cartesian system. In Cartesian system, later on we will discuss even polar system. This is in Cartesian system. So the first one, PT, which is length of tangent, and Pn, length of normal, and then TQ, length of subtangent. and Qn, length of subnormal. We have certain formula for them. Just take a note of this formula. Length of tangent is equal to y root of 1 plus 1 by m square, where m is my dy by dx at the point P. At whatever point you are considering, at that point, if you take slope dy by dx, it is my m. So the expression for length of tangent is y root of 1 plus 1 by m square. Length of normal is y root of 1 plus m square. Length of subtangent is y by m. Length of subnormal is y into m. Y into m. You have to remember. How to remember is up to you. How to remember is something is up to you, but you have to remember at any cost. There is no other way out. Okay? Or else, what only you can do is, we should know how to derive an expression for this. Y minus y1 equal m into x minus x1 for the equation of tangent, and for the equation normal also you know what it is. Okay? But instead, if you remember them, you can do things very fast. And along with these 4 expressions, we have some more expressions which are important. For example, if I take this as O, origin, this OT in fact is nothing but x-intercept of the tangent. X-intercept of the tangent is my OT. X-intercept means the line wherever it crosses x-axis, that point, its distance from origin is my x-intercept. Similarly, this would be, suppose this is maybe m suppose. OM would be what? Y-intercept of tangent. Y-intercept of tangent. X-intercept of tangent is given by x minus y into dx by dy, and y-intercept of tangent is y minus x into dy by dx. Y minus x into dy by dx. This is nothing but y minus mx. Y-intercept is c only, in y equal mx plus c is the y-intercept, which is y minus mx only. Okay. And apart from that, one thing which is important, which I asked you to learn already, is radius of curvature. If you remember, what is that? 1 plus y1 square whole power 3 by 2 by y2, where y1 is first derivative at the point P, y2 is second derivative at the point P. At a given point, these are all about at a given point, any given point P. Okay. And one last thing, suppose there are 2 curves which are intersecting. 2 curves which are intersecting curves. Okay. At the point of intersection, what is the angle between these 2 curves? Angle between the 2 curves at the point of intersection is always equal to angle between the tangents drawn at the point of intersection. So if I draw at this point for this curve, if I draw tangent, it looks like this. For this curve at the point, if I draw tangent, it looks like this. The angle between them is this theta, or it can be 180 minus theta also. Both are thetas, both are angle between the 2 straight lines, angle between the 2 curves itself, right? So it might be theta or 180 minus theta. So theta can be a acute angle less than 90 degrees or an obtuse angle which is greater than 90 degrees. So that theta is always given by tan theta equal to m1 minus m2 by 1 plus m1 m2, where m1 and m2 are slopes of those two tangent lines at the point of intersection. So if this is M1, this is my M2. Angle theta between the curves at the point of intersection. Angle theta between the curves at the point of intersection is given by tan theta equal to M1 minus M2 by 1 plus M1 M2. Why only M1 minus M2? Why it should not be M2 minus M1? It can be M2 minus M1 also. Depending upon which one is bigger, which one is smaller, you will get acute angle or obtuse angle, and both of them are angle between them, or sometimes we also refer to as M1 difference M2. M1 difference M2. Or else sometimes people, if they want only acute angle, they take mod M1 minus M2. If they want only acute angle, they take mod M1 minus M2. If you get it negative, tan theta comes out to be negative, means you will get greater than 90 degrees angle, which is an obtuse angle. Okay, whatever, that depends on the case. Okay, and this and this are extremely important one. We keep using them. This I said already that this is, we are going to use this later on also. And this is something which is very important, because sometimes, you know, that angle theta might be 90 degrees. When the angle theta is 90 degrees, it means that you are talking about an orthogonal curve. Ortho 90 degrees, orthogonal curve to the given curve. Given some curve 1, suppose, find a curve which is orthogonal, which intersects this curve orthogonally. Which intersects this orthogonally. Therefore, obviously at the point of intersection, the angle between them would be 90 degrees, in which case M1, M2 equal to minus 1. Suppose if M1 is slope of this one, which is dy by dx of first curve, then dy by dx of second curve would be minus 1 by dy by dx, and then proceed further, whatever. Take a question. Find the equation of the curve which passes through. Find the equation of the curve which passes through. Find the equation of the curve which passes through 2a comma a, for which the sum of the Cartesian subtangent, and the abscissa, the sum of the Cartesian subtangent and the abscissa. So Cartesian subtangent means this. Cartesian subtangent means this, y by m, y by dy by dx. And abscissa, what is abscissa? X coordinate of the point is called abscissa, y coordinate of the point is called ordinate. Abscissa and ordinate. Given a point x comma y, x is called abscissa, y is called ordinate. Okay. Right now, the sum of the Cartesian subtangent and abscissa at the point, continue, is equal to a constant a. Is equal to a constant a. Is equal to a constant a. Okay. So what it has given? The sum of the Cartesian subtangent y by m plus x equal to a, which in fact is y equal to a minus x into m, which is dy by dx, which gives me a first order and first degree ordinary differential equation. So a geometric scenario, when it is converted into symbols, it becomes a differential equation. A differential equation is nothing but a scenario, basically, a scenario wherein that scenario, if you try to convert into mathematical symbols, it brings a differential equation. If you solve the differential equation, which gives me curve or a family of curves which reflects that geometric scenario, right? Okay. Now, this is something which you can easily solve. Therefore, this is 1 by y dy is equal to 1 by a minus x dx. is a first order, first degree ordinary differential equation, integration of which gives me the complete solution. So I will take it as log C here, because I definitely know on integration will get logs. So log y equal to minus log of a minus x plus log c, which gives me y into a minus x equal to c. Y into a minus x equal to c is the family of curves which satisfy the given geometric condition. And one more thing is given. What is that? The curve passes through 2a comma a. One passes through 2a comma a. Therefore, a into a minus 2a equal to c, which implies c equal to minus a square. Therefore, the required curve is given by y into a minus x plus a square equal to 0, which exactly is the curve which is the required ones.